Okay everyone, this is part 2 of lecture 3, just continuing on. So I've talked a little bit about how you work out the formula for, or formulae for ionic compounds. The next thing that we've got to do, of course, is give them some sort of a name. So this is just giving you a brief overview of how you name these ionic compounds. The rules are actually pretty simple. So here they are. The first one is that you write the name of the metal first. Of course, as I've already stressed before, all ionic compounds are going to have one metallic component, that is one metal, and they're obviously going to have one non-metal, otherwise we can't get this give and take arrangement with electrons. So the metal name is always written first. Obviously the non-metal name is then written second. And the other thing that you have to keep in mind is that the non-metal, that is the thing that's picking up the electron, that is, that it's an anion. It's the suffix of the word or the name of that particular anion is going to get changed to "ide." So perhaps what we could do is best give you some examples for this. So what is the name of the following ionic compounds? Well, you can see all there, of course, they're all written with the metal first. So for the first one we've got sodium chloride, so it's NaCl sodium chloride, and of course the name chlorine is changed to "ide" because it's the non-metal. There it is. The next one is copper fluoride. The next one is aluminium chloride, copper nitride. So there you go. Now the other thing that I want to point out to you that's very important is that there are situations where groups of atoms stick together in chemical reactions and don't tend to break apart, and they've actually got a charge on them. So these groups of atoms, obviously there's many of them, and poly means many, so these groups of atoms get around as what are called polyatomic ions. Now I want you to be aware of just a couple of them, or a few of them. The list is actually quite long for these, but these are the ones that I want you to be able to remember. Hang on, if I just go to my pen here, I might need this. So the first one that I want you to remember is nitrate. There it is there. What does it look like? Well, it's got a nitrogen atom stuck to 3 oxygen atoms, and there's a net charge of 1-, so it's written as NO3 with a superscript minus sign on it. So if you were to refer to a compound which was ionic, clearly this would be linked up with a metal. This is actually, if you like, you can regard this as the non-metal component, and the metal in this case is sodium. So we've got this compound here called sodium nitrate. Notice, importantly, that there's no charges written in this compound, but implicit in the information here, not actually written out, is, whoops, that's a minus, that sodium ion is +1, and of course the nitrate ion is 1-, and that's the case, of course, with all ionic compounds. They're not often written with the charges on them, but nevertheless you should be able to recognize that that is indeed the case, that one of them is going to be a positive cation and the other one a negative anion. If we look at the next one, carbonate, here it's CO3. In this case it's got a 2- charge associated with it, so it's superscripted with 2-. And the example that we're giving here is copper carbonate, Cu, CO3. And again, I can't stress enough that these things, implicit in here is that these things have charges on them. The copper, of course, would be 2+, and this carbonate ion here is actually 2 minus. Sorry about the mouse work, it's not very good. Sulfate, there it is there, and so that's the formula for something like silver sulfate. I'll also point out to you that you have to make sure that overall the compound is electrically neutral. If sulfate has a 2 minus charge on it, if you look up the valence for silver, it's normally 1, i.e. it's 1 plus, so therefore you need 2 1 plus silver ions to balance out the 2 negative charges on that sulfate group there. If we look at hydroxide ion, it's a 1 minus, so if we have something like calcium hydroxide and the valence for calcium is 2, then to balance everything, to make sure overall the charge is neutral, we need 2 hydroxide ions, that is 2 minus charges, to balance out the 2 plus calcium ion here. So we have to put the hydroxide ion in brackets and subscript it with a 2, showing that there's indeed 2 lots of hydroxide ion. We've already done that one. Well, not quite, but if we go back to here, oh yes we did, it was that one. So we've got calcium hydroxide here. There's no point talking you through that one again. You've got the answer in the previous slide. Okay, now the last thing I want to do in this particular lecture is just point out what all this means. How do these theories of electrons being swapped in ionic compounds and the formation of negative and positive charges end up with something that explains what happens in everyday life? So that's what this slide here is supposed to explain to you. So what's happening here? Well, if we think about a compound like, oops, go back here again, get that pen going. I don't know what happened to my pen then. If we go back to this idea, we've got a ionic compound like sodium chloride. There we go, like that. Brilliantly written, I may add. Okay, so we've got sodium chloride here. We've got positively charged cations, negatively charged anions. You all know, I think, that opposite charges will attract one another, and the same charges will tend to repel one another. So if you imagine that you've got a whole bunch of sodium ions and chloride ions together, they're going to try to rearrange themselves in such a fashion that the sodiums are as far away as possible from all the other sodium ions, the chloride ions are as far away as possible from all the chloride ions, and yet there's a close proximity here between the opposite charges. How do they do that? Well, if we think about it in 2 dimensions, it would look something like this. So here we have the chlorine or the chloride ions here, the negatively charged ones. Here we have the positively charged sodium ions. And if you look at any given sodium ion, I think you can see that it's actually surrounded by a chloride ion. There and there. So for example, this sodium here is surrounded by these chloride ions here. Alternatively, if you look at a chloride ion, you should be able to see that it's always surrounded by sodium ions, like that. So ionic compounds, when they combine chemically, form this regular system of sodiums and chlorines, of sodium ions and chloride ions, to, as I said before, maximize the contact between the opposite charges and minimize contact between like charges. If you look at the compound in 3 dimensions, then it looks more like that, but the same system applies. If you look at it, what you will see is that there tends to be an arrangement so that chlorines maximize their distance away from one another, that is the chloride ions. Same with the sodium ions, but they tend to minimize the distance between the opposite charges. What that means in reality is something like this. Ionic compounds tend to form regular lattice structures, they're called, and they translate into crystals. So here's an example here. This ionic compound is actually, I don't know if you can see this, but it's manganese carbonate. So in this case we've got a polyatomic ion, but nevertheless it's an ionic compound and it forms these crystal structures. You can imagine here on one of these planes you've got this sort of arrangement going on here. So what that means is ionic compounds tend to have quite high melting points because the particles are ions which are stuck together with quite strong attractive forces. So to pull them apart you need a lot of heat to do so, so therefore their melting points are actually quite high. They form crystals. They tend to be brittle, so that when you try to if you hit them, for example, they tend to shear off on these fracture planes here, and it's not surprising when you look back and you think about what the atomic structure of these things would be. So that gives you a bit of an idea of the properties of ionic compounds. Again, I repeat, they're going to be brittle, they're going to have high melting points, and so, for example, sodium chloride has a very high melting point. I think it's up near about 1,000 degrees Celsius. Okay, and that's what my final slide there is showing you. It's just, if you like, a little summary. The bonds between the ions are strong. The salts have therefore salts, that is ionic compounds, have high melting points. The bonds are rigid, and therefore the salts are brittle and they shear off. And of course, because of that irregular structure, they shear off into these fracture planes. There's some other YouTube videos for you to have a look at. I hope that you've enjoyed this lecture. See ya.